Okay, so next, let's talk about the gradient descent algorithm in more details. So, when we are training a deep learning model, we need to use this gradient descent algorithm to help us to learn the parameters or variables of the model architecture. And the learning process normally involves this iterative updating, right? However, different from the simple toy example we showed in the previous page, the optimization of the deep learning models will involve the optimization of some functions, and the function we use in learning the model is normally the loss function, right? So in the previous lecture on machine learning, right, this basics, we also provide you with some information about how to define some loss functions, right, for learning the models. And let's assume we have a loss function denoted by this L theta, and this theta denoting this model variables to be learned. This is L denoting the loss function, and this loss function is defined for some variables of the model, right, to be learned. And we want to minimize the loss function in most of cases. So for the classification problem we are studying for in this course or for the projects, we are doing the minimization of the loss functions. However, for some other learning problems, like the reinforcement learning, we have to do the maximization of some reward function instead, which will be slightly different. But here, let's assume we are doing the minimization of the loss function, and we want to find the optimal variables which can introduce the minimum loss values for the function. And this theta denoting the variables. Normally for deep learning models, we have so many different variables to be learned simultaneously, right? In other words, this theta can be a vector of all the variables to be learned in the model. So the gradient descent process will involve the iterative searching, right? And we have to initialize these variables with some initial values. And the normal way we do the initialization is via some random initialization. And we can denote these initial values for all the variables to be theta 0. And the remaining step will be very similar to the toy example, and it will incorporate this iterative variable updating process, and we can calculate the loss function with regards to the variables at the current location. In other words, we can calculate the current gradients for the loss function regarding to the variables, right, at the current location, like x, like theta I. This I denoting this iteration number, the i's iteration we are working on, right? And then we can denote the current gradient to be gi. If we are studying the multivariable based gradient descent, then this gi will be a vector for all the gradients of all the variables, right? And then we can do the updating of the variables according to both the current gradient as well as its current value. And we update according to the equation we show here. We have theta I plus 1, the new theta to be theta I minus alpha times gi. Depending on the gradient and its current location or the value for the variables, then we can update it, right? And this alpha denoting the learning rate for the updating process. And we will continue with this process until convergence, and then we can return this theta n to be the final output, right? Because we achieve the convergence, we assume we should stop here, and we are reaching the minimum. And actually, it depends on the function we are starting for the loss function. And if the loss function is a convex function, then we can ensure this theta n will achieve the global minimum for the function, right? However, if this loss function is non-convex, we can only ensure theta n will achieve the locally optimal result or optimal values for the loss function instead. So on the right hand side, we will show you with a curve of illustrating the learning process of this gradient descent with these multiple variable functions. And we can show you the updating process. Let's assume we are doing the surging starting from this point, and according to the gradient of this loss function regarding to the variables, we can updating or we can moving this point gradually stepwise until we can reaching the convergence point, which will be the minimum, right, for this function. So in the previous page, we are starting a very simple function where the function is convex. In other words, we have one single minimum, which will be the global minimum, right? However, in the real world, the function we are studying will be much more complicated. It will be not necessarily convex, actually will be non-convex in most of cases. In other words, for this function, if we are optimizing the function based on the gradient descent, actually in most of the cases, we cannot achieve the global optimum. So what is the difference between global optimum and local optimum? Let's assume we are studying a more complicated function instead, as shown by this curve, right? At this curve, we have, multiple local minimums, as shown here. If we're doing the gradient descent according to the gradient of the curve function, and we can move forward, right? And we can achieve the convergence at this point because its gradient will be 0 at this point, right? Similarly for this point, it will also be a convergence point if we are doing surging from here, right? Instead, if we are doing surging from here, then we can achieve the local minimum to be this point instead, right? And if we were doing surging from here, then we can achieve the minimum to be here, right? However, among these 4 different minimums, we're going to have one single global minimum, right? This one, right? And the remaining 3 will all be the local minimum instead. In other words, according to the gradient descent algorithm, we can ensure we can achieve the convergence at some minimum points. However, if it is a global minimum or local minimum, we cannot guarantee actually. So the convergence point of this algorithm for the loss function actually depends on the initialization of the variables, I mean the theta 0, right? Depending on which region we initialize is theta 0 and for the surging starting point, then we can achieve different minimum points actually. If we are doing the initialization in this range, then we can achieve this local minimum. If we're doing the initialization in this range, then we can achieve this global minimum instead, right? So it is controlled by the initialization. That's the reason why this initialization will be very important for your optimization. However, the current case is that we have no good solution to find the very good initializations. The only way we can do is to try different initialization methods at certain starting points instead. So for your project, when you're doing the model learning, you also have to initialize your parameters, which is normally controlled by some initialization method. For example, we can initialize these variables according to the normal distribution or Poisson distribution, right? And we have different ways to initialize these parameters. So in the real-world applications, this gradient descent algorithm will normally converge to the local optimal and cannot guarantee we will achieve the global optimal actually. And on the right hand side, we also show the multi-variable loss function as well. It will be more complicated and we have much more different local maximum or minimum instead. And if we are doing the surging from some regions, in most of the cases, we achieve the local minimum or maximum instead. Okay, so this is about initialization effects on the optimization process. Another important factor we need to consider is the learning rate. Before we have mentioned that this learning rate will control the updating speed of the gradient descent algorithm, right? And in this page, we will show you the impacts of different learning rates on the updating process of the gradient descent algorithm. And let's assume we are doing the minimization of a loss function according to some variable like theta. And this is a y, that's j theta denoting the loss function. And we want to achieve the local minimum for the loss function by learning the optimal theta risk variables. And in this page, we show you with different learning rates. On the left-hand side, we have a very small learning rate. And on the right-hand side, we have a very large learning rate. And for the central part, we have just the right learning rate. According to the curve, we can find that this impacts of the learning rate will be very significant on the learning performance of this algorithm. For example, if we are starting all the surging process from the same point, the yellow dot, and if we have a very small learning rate, then this updating process will be very slow, right? Because in each step, we just move this variable slightly, right, according to the gradient. The step is very minor. If we want to achieve the convergence to here, this region, we have to move so many steps, right, until we can achieve convergence. So a very small learning rate will require many updates before we can reach the convergence, right? And on the right hand side, we have a very large learning rate. A large learning rate means we can update this variable with a very large step instead. If we are still starting from the same point, according to the gradient, we know its gradient will be negative, right? Because it is decreasing. So by calculating its current gradient and also assigned with a very large learning rate, then we can update this variable from this point. Maybe we can just jump over the convergence point and to this hand side instead, right? Because this learning rate is so large, we just jump over the minimum points and to the left hand side. And then according to its current gradient, it will be larger, right? Because this gradient is so sharp. This decreasing trend is so sharp. If we further do the updating from this point, and with a very large learning rate, we can even jump over the minimum again and to a far away point, right? In other words, if the learning rate is so large, actually it is high and likely we cannot achieve the convergence in the updating process because we just do the jump over, right? And this learning process will be just like a zigzag. We just jump over the minimum points over and over again. We cannot achieve convergence. So a too large learning rate will cause drastic updates which lead to divergent behaviors actually in the learning process. Then let's come to the just right learning rate. If we are assigning a just right learning rate and we are doing updating from the same points, because for the initial points, the gradient will be larger, right? So we can move on very far away. And as we converge to the minimum point, because the gradient will be slower here, right? And if we have just right learning rate, then we can achieve the convergence with less steps than the low learning rate. And we can achieve the convergence compared to the low convergence for the large learning rates, right? So from this figure, we want to show you that the impact of the learning rate on the performance for gradient descent will be very big actually, and we have to assign a just right learning rate. However, in application, we have no way to decide the learning rate by ourselves before we try them, right? The only way is to try different learning rates and select the one which works better for your problem and for your data and for your model, right?